about the electrons. So now we're going to talk about the quantum numbers, how the electrons are arranged in an atom. So the location and the energy of every electron in an atom is determined by a set of 4 quantum numbers. We have the principal quantum numbers, n, also called as the level of energy or main level of energy, angular momentum quantum number, L, or sublevel. And then we have magnetic quantum number, m sub L, and the spin number, m sub s. So the first is the quantum numbers of orbitals. So that is important to know. That is the energy level. So the energy level can vary from 1 to 2, any positive numbers from 1. So I have 1, 2, 3, 4, right? And also, let me grab a pen over here, which make my life easier over here to talk to you. And we have this, the between levels reflects the distance of the electrons from the nucleus. Look here in this diagram, and I'm using the Bohr diagram. So the first is very close to the nucleus, so the attraction between the positive charge and the proton over here and the negative charge of the electrons is really strong. So when you getting far away from the nucleus, so that this attraction is getting smaller, so the energy is increasing. So increase the energy of the electron over here. So the higher NS, the further away from the electron is from the nucleus, higher is the energy. And if you look to the periodic table, we have 7 rows over here, and this we gonna take in consideration as the level of energy. So level 1, 2, 3, 4, 5, 6, 7 levels of energy. If you ask me what is this letter, states 4, because in the past they used letters instead numbers. Today we're gonna use numbers, so this is why I call them quantum numbers. Okay, so the numbers depend on the value of n. Which number is this? That is the subshell or sublevel L, the angular momentum quantum number. So this, when you talk about this sublevel, so they're gonna take values from 0 to n minus 1 over here. So that means if you have the first level equal 1, so L only can be 0 because it's 1 minus 1 is 0. So this is the only sublevel we can have. Okay, and the sublevels we use letter as well. So will be the letters S, P, D, and F. Do we have more sublevels than this? Yes, we do. But for the elements that we know, that are the sublevels that are always fulfilled, but can be fulfilled. But we know also when the letter get excited, they jump from one level to a highest level of energy. So if you have electrons on the sublevel F, if they get excited, they will jump for another sublevel further than this. But this is when we work with higher energy electrons. Okay, so we have sublevel S, and I want to just highlight one thing over here. This is the shape of the region where we can find an electron. Okay, so orbitals are the places or the region that we have a high probability to find the electrons. And we have L equal 1, which is the p orbital, and also the D and F. Okay, if you go over here, you're gonna see the shape of the S sublevel, which is spherical, and we have a dumbbell over here, and we have D and F. There are more complex. We have a pair of dumbbells, and then we have more over here. Okay, so we have 0 to 3 over here. So it's L, it's always n minus 1. Okay, so if you go over here, you see that when you have a P, the area, the region can be in the X or Y or Z. So we have three different orbitals, different regions that we can find the electrons. So we have three orbitals over here. Okay, here we have, look at the regions that we can have over here in D. So we have 5 regions. And here we have 7 regions that we can find our electrons. So we have 7 orbitals. Then we need to talk about magnetic quantum numbers that actually, if you think about the direction where you're going to find the electron in an atom, that could be the number of the house. So we have L, so that the first, the number, the main energy level, N, which tells you, okay, we live in Orlando. And then we have L, that we're going to tell you, you live in this street. And the quantum number tells you the number of your house. That is the way that you're going to locate your electron over here. So when you have L equals 0, ML only can be 0, because if you go to the sphere over here, it doesn't matter if you move with this sphere, the electrons will be always in this region inside of this region over here. Okay, they're occupying all the X over here, X, Y, and Z. So we only have one magnetic quantum number. But if you go to P, remember, it can be in this region, or this region, or this region. So we have 3 different orbitals. Look, ML will be from L, negative L, to positive L. So we have negative 1 to positive 1. Don't forget to pass through the 0. Okay? So if you have, you can use the formula, but I don't think it's a good idea, because maybe you get confused with this. So it's only think about we go from negative 1 to positive 1, negative 2 to positive 2, and negative 3 to positive 3, and that is the orbitals that we can have. I showed you why, because they have in different position. So sometimes you have the dumbbells and the X position, or Y or Z, so the regions are different. So we have 7 different orbitals that we can find when we have in the orbital F, okay, and electrons. So 0 will be always there, so don't step on the zeros, okay? So, and then we have the quantum number spin. And this comes from the Pauli exclusion principle, that states that in an atom or molecule, no 2 electrons can have the same 4 quantum numbers. As the orbital can contain a maximum of only 2 electrons, the 2 electrons must have opposite spins. That means when you assign an electron in this direction, the other one in the same house must be in the other direction. So one is assigned sign up, positive half, and one down, negative half. Okay? So because they rotate in opposite direction, creating magnetic fields that attract each other, thus the force of attraction, which is magnetic, and the force of repulsion, which is electrical, are counterbalanced. So they will not repel each other, they will not attract to each other. Okay? So now we learn that each orbital can hold 2 electrons, but they must be in opposing directions. Okay? And how we're going to do electron configuration over here. So electron configuration is writing the following order: energy level. So we start with the lowest energy, and every single element when they start over here. So remember, let's talk about this will be the streets, and then we have the number of the house where the elements located at, and we have a number of electrons and the orbital. So don't put commas or lines when you're writing the electron configuration. So we have the energy level first, then we have the orbital sublevel, and then we have the number of electrons in this sublevel. Okay? To work with the electron configuration, you can use the alphabet principle diagram. So the alphabet diagram shows you the electron configuration in when increasing the energy over here. So the electrons are arranged about the nucleus in a regular manner. The first electron feel the energy sublevel closest to the nucleus. And we continue filling each sublevel until it's full, and then start filling the next closest sublevel. Okay? So the orbital are filled in increasing order of energy. So we can start 1s, and then 2, 2p, 3s, 3p. So increasing energy. This is important. See here that we have more energy levels. Okay. So let's go to helium. I could use the alphabet diagram, but I want to use the periodic table as I explained it to you in the first video. So if you go to the row 1, so that will be the first level of energy. So in the first level of energy, you have to pass through all the elements you have. So we have block S in the periodic table, have block D, we have block P, and we have block F. So in this block S, we have 2 elements in the first level of energy. So I have a 1. So the first level only have, if it's 1, will be only sub-level S, right? This is the blocks that we have over here, right? So we have, 1s, and since we have a 2, will be 2. Okay? So 1s2. If I want to write down all the quantum numbers for everything, so 1 is the level of energy. So one of those electrons, so let me draw the orbital over here. I have in this direction and the other in the other direction. Remember this? Exclusion, Pauling exclusion. So, okay, so L, we know that L is what? N minus 1. So L is 0, which is the orbital S. So it's 0. ML is over here, right? Goes to negative L to positive L. So it's 0. So I only have 0. So ML is 0. MS, so up, first electron, positive half. Okay? So then we go to the second electron. So we're going to have in the same level, same sub-level, same M sub L, but different spin. Okay? Easy. And good. Okay. So when filling degenerate orbitals, the most stable configuration corresponds to the one that presents the largest number of electrons with the same spin. So electrons fill each orbital singly before any orbital receives a second electron. That is Hund's rule. So that means if I have 1, 2, 3, and I have 5 electrons to fill out this. So I'm gonna have 1, 2, 3, 4, 5. You cannot, let's put a 6, just to, 6, no, 4, just to help here. So I cannot do this 1, 2, and then 3, 4, and leave one blank here by itself. So I have 3 orbitals, remember? So this, it's wrong, okay? Because we need to take in consideration the energy. So Hund's rule, okay? So let's go to this one. Indicate 4 quantum numbers for the most energetic electron in copper. So you can use the diagram and do your electron configuration over here, okay? Or you can do to this diagram and let's go over. We have 1, 2 electrons in the first level, 2 electrons in the second level, but we have a sublevel P as well over here. So I have more 6 electrons over here, and you're gonna go over until you have 29 electrons, okay? But also you can use the periodic table in your favor. Remember, first you locate it where the copper is located at, and then you're gonna start counting. Okay, so I have the first level over here, then we have the second level, third level, and fourth. I know the copper is in the 4. So let's count together. And the first level of energy, I only have block S. So it would be 1s, and I have 1, 2. So it would be 1s2. And then I go to row 2, we can call streets, remember? And these streets we have a block S, so 2s, and I have 2 houses over here. And they're gonna keep going in the same street. I have block B, and I have 6, 1, 2, 3, 4, 5, 6 electrons in the block B, so 6 houses. And then we go to 3, so 3, we have block S over here, which has 2 houses, and they go to 3, we still have P, block P, you have 6 houses, and then go to 4. So we're gonna pass to block S, but we have 2 houses, and the copper is located in the D, but look at this. Block D, we decrease 1 level. That means now I have 3 instead 4, because 4 minus 1 will be 3. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's D 9. That is the electron configuration. Good? So if I have to fill out this, let's go let's go back over here and let's fill out this. So I have D9, right? That is the most energetic because it's the last one over here in the spin. So N is in the 3. So it will be 3. And L will be D, which is what? 3 minus 1, which is 2. So it will be 2. And ML, remember, we have from -2, so -1, 0, +1 to +2. So, and I have 9 electrons to go over here, to distribute over here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So ML will be +1. And MS, it will be +0.5. Okay? Good? Okay, so can I have ML equal +3 when I have L equal 2? No, right? Because it will be from +2 to -2 or -2 to +2. Okay, so pay attention on that. Okay, so let's go, keep going on this. So just a reminder how we're going to do the electron configuration, and you write down electron configuration, the last level of energy that include S and P sublevels containing the valence electrons. So I know this element is 7 valence electrons, so I know that is in group 17, right? And if I go to level 3, which is over here, and go to P5, 1, 2, 3, 4, 5, I know we talk about chlorine. Okay? So